Have you ever tried to run a powerful new AI model on your own machine, only to find out it's way too slow or just won't fit in memory? Yeah, it's a super common problem. The best models often feel like they're locked away in these massive data centers, totally out of reach for everyday use.
It seems like every week we hear about a new model with hundreds of billions of parameters that's breaking all the records. But that massive scale, it demands a ridiculous amount of computational power. So the real question for anyone building with AI is, how do we get all that power out of the lab and into a real application?
Well, that's exactly what we're going to break down today. By the end of this, you'll understand the core ideas behind making these giant AI models smaller, faster, and actually usable in the real world.
Okay, let's get into it. The whole challenge boils down to this. Large models need a ton of memory and processing power. So an entire field called model compression has emerged to solve this exact problem.
So why bother compressing them? The reasons are really practical. First, we need to shrink the model's file size, so it doesn't take up so much disk space. We also need to reduce how much memory it uses when it's running. This helps lower the latency, which means you get faster predictions for things like chatbots. And maybe most importantly, it's what lets us run powerful AI on small devices, like your phone. To get our heads around this, we're going to look at two main strategies. Think of the first one as a way of teaching, and the second one as a way of simplifying. Let's start with that first approach, which is called knowledge distillation. And honestly, the best way to think about it is like a master teaching an apprentice. So you have a teacher model. This thing is huge, it's complex, it's incredibly accurate, but it's also really slow and expensive to run. Then you have the student model. It's much smaller, way simpler, and the goal is to train the student to perform just as well as the teacher, but without all the complexity. Now, here is the really clever part. The student doesn't just copy the teacher's final answers, like cat or dog. Instead, it learns from the teacher's reasoning. It looks at the full probability scores, sometimes called soft targets, to understand why the teacher thought it was 90% a cat and only 5% a dog. This gives the student a much richer, more nuanced lesson. So, to put a formal definition on it, knowledge distillation is a process where you're actually creating a brand new, smaller model architecture. It involves a full retraining where the student learns from the teacher. The end result is a compact, specialized model that has inherited the wisdom of its much larger mentor. All right, let's switch gears to our second technique, which is called quantization. This one isn't about teaching a new model. It's about making the existing one simpler. The intuition here is pretty simple. Imagine you have a number with a ton of decimal places. Quantization is basically like rounding that number. Sure, you lose a tiny bit of precision, but the number becomes way easier to store and to work with. So here's how it works under the hood. A neural network's weights are usually stored as very precise 32-bit numbers. Quantization is the process of converting those high-precision numbers into a much lower precision format, like an 8-bit integer. This change has a huge effect on memory and speed.
And the impact is pretty massive. Just by going from 32-bit floats to 8-bit integers, you can often cut the model size by 75%. Plus, processors are just way faster at doing math with simple integers. And the best part? This usually happens with a surprisingly small drop in the model's accuracy.
So the key thing to remember here is that quantization doesn't change the model's architecture at all. The original model stays exactly the same. You're just changing the format of the numbers inside it. It's a much more lightweight process than the complete retraining you need for distillation. Okay, so we've got the two core ideas down. Now, where do you actually see this stuff being used, and why should you, as a practitioner, care? The truth is, compressed models are everywhere. They're what make real-time chatbots feel instant. They are the reason you can have powerful AI features running right on your phone or in a smart speaker. And for any business trying to deploy AI, they are absolutely essential for keeping costs under control. So let's just quickly put them side by side. Distillation is about knowledge transfer. It creates a whole new, smaller model through retraining. Quantization is about reducing precision. It keeps the original model, but just simplifies the numbers inside. Distillation gives you a highly specialized, small model. Quantization gives you a quick win on size and speed. And here's the thing. You don't have to choose just one. In fact, a really common workflow is to combine them. You first distill a huge general model down to a smaller, specialized one, and then you quantize that student model to squeeze out every last bit of efficiency.
If you boil all of this down to a single sentence, it's this. Model compression is what makes large AI practical. It's all about trading a tiny bit of performance for huge gains in speed and size.
And that really is the key takeaway. This isn't just about making models smaller for the sake of it. It's about making a deliberate engineering trade-off between a perfect model and a practical one that can actually run where you need it to.
Which leaves us with a question that every engineer faces. For your specific problem, how much perfect accuracy are you willing to trade for speed, for lower cost, and for the ability to run your model anywhere? That choice is at the very heart of building useful AI.